Very well. So, so we talk about the Hodge locus that was mentioned, and yeah, and in this setting of Hodge locus, I will tell you about these typical versus atypical intersections. But I mean, if you were to get lost, I mean, typical, you should think something like that, like this. So you see, like, there are two plane curves in the projective space of degree 2, degree 4, one of degree 2, one of degree 4, the other, and they intersect in 8 points. Nothing atypical here. And in fact, yeah, do you know who proved this theorem?
Not Hodge.
Not Hodge.
Bezout?
No, not Bezout. Well, Sir Isaac Newton. Yeah, so that's there's some physics there as well. And what's atypical? Yeah, atypical, well, it's harder to draw, and I will have better pictures, but maybe one example that you could be thinking of. So we are in a three-dimensional space of all theories. And maybe there's a string theory is one-dimensional. And maybe Hodge theory is also one-dimensional. And it turns out that they intersect, but two lines in a three-dimensional space, they shouldn't intersect. So maybe that's an atypical intersection. Great. So the goal is to give you three points of view on the Hodge locus. The first one, without Hodge theory, in fact. I mean, so it can be defined in some cases fully algebraically. And I will explain that thing. The second one will involve Hodge theory, which is needed to define these typical and atypical intersections. And finally, I try to collect, to make it maybe more interesting to everybody, I try to collect what I know of, like the relationship between the Hodge theory and string theory in general, and I will present a few examples. So yeah, and but yeah, we will see when we get there. So this theory is born in algebraic geometry. So what's algebraic geometry? Well, people normally study solutions of polynomial equations. So what's the simplest example of this? It's just a hypersurface. So a hypersurface of degree d and dimension n is simply the zero set in some projective space of n plus 1 variables, of dimension n plus 1, of a homogeneous polynomial f of degree d in n plus 2 variables. So it's really cutting you a variety of dimension n. And of course, this is not, it's very weak, and we care more about smooth hypersurface, and smooth just means that the partial derivatives of f don't simultaneously vanish. And now you consider these things in c to the n minus c to the n plus 1 minus 0 rather than this empty space. So well, just one example. I mean, it's like a curve of degree d, very famous for any d, is just in the projective space, you just sum x to the d plus y to the d plus z to the d equal to 0. So that's homogeneous of degree d, and it has some genus associated. Yeah, but we can study higher dimensional objects as well. So one goal in algebraic geometry is to understand a variety, whatever it means, and one way to do it is to understand a higher dimensional variety by looking at lower dimensional subvarieties. So for example, we feel like we understand curves well enough, somehow there are a bunch of invariants associated with it, and then we can say, okay, now how do I understand a surface? Well, I study all the curves inside my surface. How do I understand a threefold? I look at all the surface, all the curves, and so on and so forth, and eventually gain some knowledge by doing this trick. But okay, so now let's say we want to study hypersurface, so we fix some dimension and degree. First of all, we should understand kind of a behavior on average, some sort of generic behavior. And to do so, we need to compare hypersurfaces one to the other. So that brings us to some notion of moduli space. And in this case, it's very easy. So, well, a hypersurface is just the zero locus of a polynomial, so it's essentially a polynomial. And a polynomial is just a point of a complex vector space, the point of homogeneous degree d polynomials in these n plus 2 variables. That's fine. But that's just a vector space, so maybe it's not so interesting geometrically. But it becomes much more interesting if we now study smooth hypersurface, so if we remove some discriminant locus. And so our parameter space, that we call a U and D, by this dimension and degree fixed, just a vector space minus some locus discriminant equal to 0. And that guy here is parameterizing, possibly in many different ways, the same hypersurface, but it's parameterizing smooth hypersurfaces. And so the first question is, what can we say about the very general hypersurface? And very general means that we want to look somehow at generic behavior. And generic in this theory means outside a countable union of subvarieties of this UND. So this UND is really an algebraic variety. So that's how the story actually started. And there's a theorem from 1882 of Noether. And it says the following: every curve on the very general surface, X in P3 of degree D bigger or equal than 4, is the complete intersection of X with another surface. Well, why D equal to 4? I think in Pierre Deligne's talk yesterday, he gave an example with D equal to 3, and we saw that it was not the case somehow. So that was kind of already explained. So how do we prove this theorem? So what was Noether's idea? So you can consider another moduli space. So you fix n and g. Well, sorry, it's not. I mean, now we are really speaking of surfaces. So you fix n and g, and you parameterize curves of degree n and genus g on a surface of degree d. And inside this locus, you can consider a smaller sublocus given by pairs Cx, where C is not a complete intersection. Yeah. And there's a projection map just by forgetting the curve, just by reassociating X from this moduli space. And somehow Noether thought that his theorem would hold if you were to remove from UND the image of all these loci. So that's just, I'm just looking for things that are not complete intersection. If I can remove them, I will be done. So the question is whether I can find a point outside this locus here. So it looks like W and G is an algebraic variety. Rho is a proper holomorphic map, in fact algebraic. And the image of this rho W and G is a finite union of subvarieties. So probably they are strictly contained in V, and so I'm done. But here, I mean, Noether was, I mean, he didn't quite claim this, was just making some computations. So let me give you one example why you should believe that it is strictly contained in V, and it will also show that D bigger or equal to 4 is needed. So yeah, we speak, the easiest locus to describe is W10. So it's curves of degree 1 of genus 0. So it's really just, I want to describe the locus of smooth surfaces containing a line. So a line is not a complete intersection. So complete intersection means that I have my surface in P3. And I'm intersecting with some other surface. And of course, you can compute you get a line here, and you can compute the degree, but there's a degree D here thing, so you cannot quite get a projective line as a complete intersection. So how do I describe this locus? Well, first of all, I decide to fix a line, a specific line in P3, and I consider the subfamily of surfaces containing this fixed line. And in fact, using some algebraic geometry, you can describe it as a subvector space. It's like the H0 of the ideal of definition of L twisted by D inside my moduli space H0. Now, that's just the moduli space. That's just the vector space parameterizing polynomials of degree D in 4 variables. And there's a way to compute the dimension of this, the codimension of these objects. So there's some short exact sequence and define. I mean, that's essentially the definition of this ideal sheaf. And it turns out that so the codimension of this locus in my parameter space is equal to the dimension of H0, the line OLD, I mean the ideal sheaf of OL of L twisted by D, which is D plus 1. So you will have to trust me. And then now I can move my line and have a Grassmannian of lines in P3, and it has dimension 4. So eventually the codimension of my W in U to D turns out to be D plus 1 minus 4, which is just D minus 3, which is indeed bigger than 0. So it has codimension bigger than 0. So in some sense, I have my parameter space here, U to D, and I have all these things that I wish to describe them as strictly, I mean, I want to say that they don't cover the space, so I want to show that one of these guys is not cover the space. I have to show that each of them has codimension bigger than 0, and at least I've done it for the subvariety W10. Are there any questions on this point? Okay, but the computation they get more and more difficult as n grows. So here I was capable of doing it just because I had a line. And in fact, I mean, this program was completed by Lefschetz, and he introduced the so-called Lefschetz pencil and also the Lefschetz 1-1 theorem. And yeah, he said, well, I can read the quote. So it was my lot to plant the harpoon of algebraic topology into the body of the whale of algebraic geometry. So the use of topological methods, it was quite new back then somehow. And so if you combine these things, the Noether strategy and this Lefschetz theorem, you get the so-called Noether-Lefschetz theorem, and it says exactly that for d bigger or equal than 4, this locus NLD is a countable union of strict subvarieties of my parameter space, and in particular as a variety outside. A surface outside this locus will have this enjoyable property that every curve is a complete intersection. If you were to do it in an algebraic way, I mean, it would be enough. You know that this bad locus is a countable union of things. It would be enough to produce the equation of a surface outside for which you can prove that it is outside, it lies outside this locus. And if you find one equation of a surface with that property, you would be done. You would know that then the bad locus is just a countable union of things. And in fact, I mean, nowadays there's a way to compute the fact that every curve is a complete intersection. But already in degree 4, producing such an example, it was done only in 2007, and that's like one equation. But I mean, so it's easy to write equations, but it's very hard to control algebraic subvarieties, even of codimension 1. So understanding that every curve here is a complete intersection from this equation, it's very tricky. And I mean, well, that was done maybe with some computer program or something, but certainly in 1882, it was not so easy, and then the proof was very important. Are there any questions? Okay, so then we move forward and we start to introduce this infinitesimal Hodge theory, and it was developed by Griffiths. And that theory, well, I mean, Hodge theory was already kind of explained by Bruno, so I will not go into all the details at the moment, but just let me tell you what the applications to this Noether-Lefschetz locus is. So we said that there are countably many irreducible components, and we want to now understand them better in order to say something not only about the generic hypersurface, but rather than also on the exceptional ones. So we can say that for each irreducible component y of the Noether-Lefschetz locus, we have the following property. So the codimension of y in my space U to D is squeezed into a bound, which is h to 0, which is just d minus 1 choose 3. So h to 0 of some surface of degree d, and d minus 3. And this bound here, so this bound here uses some Hodge theory, but we will see it where it comes from in a moment. And this d minus 3 came from this component W10. So if you were to draw a nice picture, that's like the space, well, it's not compact, so U to D. There's the biggest in dimension component, which is W10, the varieties containing a line, and then there are many others of smaller dimension. It goes on. And notice that, so they introduced this definition, so a component is general if it has codimension h to 0, it means it's the smallest, and it's exceptional otherwise, so if it's bigger in dimension or smaller in codimension. And notice that exception, I mean, you can do the math, and the exceptional components exist only for d bigger or equal than 5. Otherwise, everything is general, because d minus 1 choose 3 will agree with d minus 3. And so what can we say about the distribution of this Noether-Lefschetz locus? So in fact, it's known that the general components are dense analytically in this parameter space. And we can even be more precise. So they have codimension bigger than 2d minus 7 with two exceptions. So the surface is containing a line, what we saw before. And the surface is containing a conic. So in the first case, they will have codimension d minus 3. And in the second case, they will have codimension 2d minus 7. So if you have a component of codimension d minus 3, in fact, there's only one. So the biggest one is really well defined. It's this one containing a line. Then there's some gap, and then you will get surfaces containing a conic, and so on and so forth. And if d is much bigger than 0 and divisible by 4, there might be infinitely many exceptional components. So there are some examples constructed by Claire Voisin on this. And with Bruno Klingler and Emmanuel Ulmo, using this unlikely intersection viewpoint, I'm going to explain in a moment, we prove that the exceptional components are not Zariski dense. So the exceptional components mean that the ones that are bigger in dimension. So the other ones are dense, but this kind of exception have some sort of finer geometric meaning. So for example, related to contain a surface, containing a line or something like that. They can appear infinitely many often, but they don't become Zariski dense in the space. So they accumulate in some fixed subspace of our period domain. So there's some subvariety W containing all exceptional. components. And yeah, well, that was a question from the 90s of Claire Voisin, motivated by some conjectures of Harris on this topic here. So unless there are any questions, let me move forward and describe how Hodge theory enters in the picture. But the first thing that we should take home from this discussion is that the noether-lashes locus is an example of the Hodge locus. So, but even if Hodge locus contains the word Hodge, in some cases it can be described fully algebraically by saying there are subvarieties containing a curve with some extra degree or extra genus. So how do we study hypersurfaces using Hodge theory? So first we introduce the cohomology group with rational coefficient associated to our space X. So that's why from a polynomial, in some sense, we need a topological space. But this is a vector space. It's just a vector space whose dimension depends only on n and the degree of f. So it doesn't quite see the richness of the polynomial f itself. But what depends truly on X is the so-called Hodge decomposition. So we already seen it. So once you tensor this vector space with C, it comes with kind of a functorial and natural PQ decomposition with P plus Q equal to N, coming from, well, we saw it coming from this kind of, well, I will not go into all the details of the story, but it comes from partial differential equations and harmonic integrals on X, and the fact that then you can take the PQ decomposition of harmonic form, it's natural and it's still harmonic. And why did I decide to tell you something about surfaces rather than maybe threefolds, since maybe most of the people in the audience are more interested in Calabi-Yau threefolds. But in some sense, to describe the Hodge locus, it feels it's easier, at least in first approximation, to do it when the dimension is even. How so? Well, because when the dimension is even, there's a preferred subspace in this PQ decomposition given by the HLL classes. So I can really do like kind of where L is half of the dimension. So. And in fact, we saw it yesterday when the Hodge conjecture was described. So whenever we have a subvariety of codimension L in our space, in our X, we obtain what's called a Hodge class. A Hodge class is just a rational, we will go back to this, but it's just a vector here, such that when you tensor it over C, it becomes of type LL. And this somehow, it's a way, it's gonna make sense, but it doesn't make sense on the nose for a threefold, for example. Because there's I cannot take the 3 over 2, 3 over 2 cohomology. And the Hodge conjecture inverts this association. So tells that the Hodge classes come from algebraic subvarieties in some sense. And the case L equal to 1 was established, so in the case of codimension 1, was established by Lefschetz using normal functions à la Poincaré, and that was already bridging from algebraic geometry in this noether-Lefschetz picture and some sort of Hodge locus picture. So more formally, so we need to work with a variation of Hodge structure. So as we saw before, so the cohomology is varying. The cohomology groups and the Hodge structure on the cohomology is varying as you vary X in your parameter space. So U and D is just smooth hypersurfaces of dimension N and degree D. So as X varies here, the Hodge structure on these vector spaces vary. And we obtain a variation of Hodge structure. Well, I've already seen it, but just to repeat it, it's a vector bundle with a connection, a filtration, a polarization, and there's a rule telling you how the connection and the filtration interact. That's called Griffith's transversality. And each fiber by fiber on this vector bundle gives you a Hodge structure. And so you can define the Hodge locus, that's really in the topic of these symmetries. You can speak of the Hodge locus as the set of closed points of your base, such that the Hodge structure living above the X has extra Hodge tensors. And I will now give you a more precise definition. So this requires introducing briefly the Tannakian perspective. So what's the Tannakian perspective? So in general, a Hodge structure is just a PQ decomposition, as this. And a Hodge class, as we saw before, is a rational element such that when you look at V tensor 1 in the complexification of this vector space, lies in HLL. That was what was happening in even weight. And now if I'm something of odd weight, I can perform some tensorial operation. So I can tensor the Hodge structure I have on V by some times, and multiply it by the dual Hodge structure by B times. And I can speak of Hodge classes inside some tensorial construction. So if I were to look at Hodge classes in the H1 of an abelian variety, there's nothing because I don't have like an HLL. but I can find Hodge classes in the H2 of an abelian variety, in the H4 of my abelian variety, or in the H10 of A cross A cross A cross A. So I'm letting myself to deduce symmetries in some tensorial construction that I perform both at the level of Hodge structures or at the level of algebraic varieties that I'm working with. And now introduce a group that's really kind of measuring the amount of symmetries of my system. So the Manforty group is simply the fixator in GLVQ of all Hodge tensors. So from a Hodge tensor, I can build a group. And this group, I can associate it both to the variation of Hodge structure and to each point. So you could think that whatever, you can think that your variation of Hodge structure is kind of a complicated system. I mean, even if you were thinking it's kind of discrete, there's a global symmetry, G, I will denote it, global symmetry. And each point X gives you a point Gx, which lies inside G, and it can be smaller. And when it's smaller, it means that X, the little point X, has extra symmetries. And we are interested in deducing, I mean, in understanding, so that's my little point X. So if you pick a point at random, you will have as many symmetries as the global system, but other points can appear to have more symmetries. And we are interested in studying the locus where more symmetries show up. Yes, please?
So when you write these Hodge tensors, this truncates, right? So they are not infinite.
But a priori they're infinite, but in fact you need only finitely many. You're right.
It's finitely many.
Yeah.
How do you? This is a purely representation theory.
That's right. That's right. But I mean, then if you ask me, if I give you a Hodge structure and you ask me for a bound of how many Hodge tensor I need to go through to find all of them, it's not so clear how to make it kind of. There's kind of, I know a priori there are only finitely many operations I need to consider, but it's not so clear to tell in advance how many.
So it doesn't follow just purely from the Manforty group.
It will, but I mean,
but it's not easy.
It's not so clear. It follows from the Manforty group and how it's kind of described somehow, but then. In fact, every group is, so yeah, but yeah, exactly. It follows from the Manforty group. But even in general theory, every reductive group, in some representation, it can be described as the fixator of a single vector. But then in which representation do you find a Hodge vector? So it's a purely group theoretical question. But how do you do it? It's not something like I can do, maybe some people can do it, but I cannot do it just that easily. So it's not, but it would be very interesting to know which bounds have to show up. Yeah, that's a very good question. Are there more questions on this picture? Even any questions is welcome. Very well. So what's known about this Hodge locus? Well, the Hodge locus is known to be a countable union of algebraic subvarieties. So in fact, this definition is kind of taking place into the analytic category, but in fact, it turns out to be algebraic. And those subvarieties that you find in the Hodge locus, they are called special subvarieties of S. And what was explained about the definability of period maps gives a new proof of this theorem as well. So by the definable setting envisioned by Baker, Klinger, and Zimmerman, you get a new proof of this, but I will explain more on that in a moment. And the general question in here is like, what can we say about the Hodge locus, and what do they tell us? I mean, what if I say something non-trivial on this Hodge locus, what does it mean for like this system or my family of varieties? I mean, like, what do they explain us? What kind of information do they hide? Let's just give an example. So the Hodge conjecture is true for hypersurfaces outside this Hodge locus. So in some sense, I mean, knowing where to find hypersurfaces where it's hard to prove the Hodge conjecture seems important. And in fact, this theorem here, at least if V was coming from geometry, it's in fact predicted by the Hodge conjecture. So when I was drawing this Noether-Lesches locus and I was describing this piece of the Hodge locus as some sort of algebra geometric, in an algebra geometric way, indeed that would be always the case if you knew that the Hodge conjecture was true. Because the existence of an extra symmetry forces the presence of an extra algebraic cycle, and I can write fully algebraically in my base variety the sublocus, I mean, as a countable union of things, the sublocus where there's an extra algebraic cycle. So the problem, it could be phrased fully inside algebraic geometry. But nevertheless, I mean, even in the theorems we saw about the Noether-Lefschetz locus, we need to use some Hodge theory. So even if the Hodge conjecture was true, I mean, we still need the Hodge theory to advance our understanding of these objects.
Can I ask another
Yeah,
thing
please,
about
please.
this? So you make this connection with the Hodge conjecture. I know, I understand how it works when it's just V, right?
Yeah.
If it is this tensor product and I give you a Hodge tensor, would you know what sort of cycle or in what sort of space I have to construct?
Yeah, exactly. But I'm outside this Hodge locus. So the link with
I mean, just the last point.
the CDK, you mean?
Yeah.
Yeah. Why is predicted by the Hodge conjecture? You mean?
Yeah. So I understand when it's like kind of directly V, but
Yeah.
if it is the tensor product of
Yeah, but so in the tensor product, there are only finite many operations that we need, so it doesn't quite matter. So I could replace my Hodge structure by some tensor construction and speak of the vectorial Hodge locus for that tensor Hodge structure. And so basically, I'm rather than considering the Hodge structure associated to the family X, I'm considering the Hodge structure associated to some piece of the self product of X cross X cross X cross X. And now use the Hodge conjecture rather than on X cross X cross X. In fact, there's something funny happening here. Thanks for the question. In this Noether-Lefschetz business locus, the Hodge conjecture seems to be known. It's just a surface. But what you don't know is the Hodge conjecture on X cross X, for example. And then that kind of wants to play a role in the theory. And we will see where it enters somehow. The fact that to speak of symmetries somehow, you cannot bound the complexity of the symmetries that you have, at least from this Tannakian perspective. So if you want to plug in groups in the game, you need to replace X possibly by X cross X cross X. But then there's a price to pay that maybe you knew the Hodge conjecture for X, but you don't know the Hodge conjecture for X cross X cross X. So that's a big price to pay, exactly. But at least it gives us some groups. And yeah, for some reason we have more tools to attack group theory rather than. Yeah. I mean, Hodge theory is a way to linearize, is a way to bring a linear algebra inside the game. So that's essentially what it does. And then, I mean, but then linear algebra is not trivial, and you have to do something with this linear algebra. And the way we do it is, I mean, is using some group theory, algebraic group theory. Thanks for the questions. Anything? Yeah, please.
When you say Tannakian perspective, like, are you talking about like some sort of category variations of Hodge structure,
Exactly.
and you take the like? So I should understand this Mumford-Tate group as the Tannakian group that comes from like the automorphisms fiber puncture of that category, right?
Yeah. So the category. Yeah. Thanks for the question. So you have two categories: the category of variation of Hodge structures, and the category of Hodge structures. And you have your object V, and you have your object Vx.
Right.
And then you can form the smallest Tannakian category containing this Tannakian category here. So it's just generated exactly. That's exactly the point why I need to take tensor products. Is the category generated by V, tensor V, tensor V, tensor V dual plus blah blah blah, and they can do the same here. And up to the choice of a fiber functor, which is, I mean, it's not gonna matter in some sense, even if it does. This category is gonna be rep Gx, and this category is gonna be rep G. And the way I'm doing it is, I'm telling you that this is an abelian category with a tensor power. I mean, like the groups are even like reductive because it's even a semi-simple category thanks to the polarization. So there's also there's all this theory that's gonna realize these things. And since I have a specialization from this one, I also have a map from this one.
Right. Okay. And that
Exactly.
corresponds to the inclusion that you have.
Exactly. Yeah, lovely. Thanks.
Okay, thank you so much.
No, that helps. I mean, I didn't know. Yeah, that corresponds to this business here.
Yeah.
So in fact, they are different, but I mean, it's like,
Right.
They're canonically included. But to make precise this inclusion here, I should give you the fiber functor here as well. So also these maps here depend on a base point. So the fiber functor from this category to the category of vector spaces is in fact taking V and associated to the Hodge structure V of X, V of S a point. So in some sense, this group depends on the choice of a point, and then you can perform parallel transport and move to a point. So if you're willing to parallel transport this point to another one, they're canonically included. So, I mean, I didn't want to go into the canonical inclusion too much.
So you get the generic Mumford-Tate group from the fiber functor over like a point outside the Hodge locus. Then
It doesn't matter.
it doesn't matter.
It doesn't matter. So the theory of Tannakian categories tells you that the fiber functor that you pick is not going to influence the theory. But nevertheless, I mean, yeah. But that's an important point.
Okay.
You're right. It doesn't depend on the point, but then it means that somehow you have to, if you want to move from one point to the other point, you have to perform parallel transport.
Oh, okay.
It doesn't depend on which point you make,
Okay.
you pick, but it's kind of a conjugation. So the up to conjugation is well defined,
Okay.
but if you want to insert the conjugation, it's going to depend on which 2 points you pick. But nevertheless, it's a fiber function from a different category.
Right.
And then on this category, if you first stop here and do the Tanakian theory here, and then you go down, then it's going to see the point. If you just go directly, the theory of Tanakian categories tells you that there's a canonical in universal form. So it's like, given 2 fiber functors, there's a canonical way of identifying them.
Thank you so much.
Thanks. No, but that helps a lot. And in fact, if you want to be precise, when you do this, you should take the connected component of this
Okay.
group. There's also, yeah, sorry, the map, yeah, you're right. The map is in the other direction at the level of representation, but then it means that there's this.
Yeah.
So this map is kind of this one. Yeah. So more invariant means smaller groups. Yeah, that's an important transition. More questions on this, please. Very well. So yeah, that's what we were saying. So did I address your question? That was.
I mean, just maybe as a remark.
Yeah, please.
I think from a physics point of view, I have no idea why one has to take this tensor product. I don't know what it means. Anyway, it's just for the physicists. Interesting.
But that's kind of interesting indeed. So
Central to the others.
yeah, but even when you speak of abelian varieties with complex multiplication, the Manforte group is going to be a torus. And it's fully defined, somehow it's a torus if and only if you have a lot of endomorphisms. But then different abelian varieties with different Manforte groups will have, I mean, even if they are CM, they can have different Manforte groups. So it depends on what kind of endomorphism, maybe the abelian variety is a product, maybe not. And then it's related to the fact that when you prove, even the Hodge conjecture for CM abelian varieties is not known. Because if you take the H4 of your abelian or CM abelian variety, there might be extra cycles there. Even though the condition of being CM is fully on the endomorphism. So it's like the simplest complexity is determining some property of the Manforte group, but not all of them. So nevertheless, even if you start with like degree 1 complexity, there's some is going to influence degree 2 complexity. Exactly. Yeah, that's. I'm glad to hear that it's tricky in physics because it's also tricky here. I mean, it's not. We don't have a rule of thumb for this. Okay, so I mean, I want to tell you about this atypical or typical. Yeah, I mean, maybe this one was not too serious, but yeah, atypical intersections are more complicated. But to do so, it's where I need to use some more high-level Hodge theory. So a variation of Hodge structure we understand is simply as a period map. So given our group G, we can form all the Hodge structure with the same symmetries as G. So that's kind of our system. And we can see our space inside the parameter space of Hodge structure. So that's kind of just a very linearized object. I mean, of course, it's modded out by the action of the integral points, but it's much easier. It's kind of it's where the linear algebra naturally lives. So that's kind of a moduli space of algebraic objects. That's a moduli space of linear objects, like linear algebra objects. And everything is hidden in this guy, the period map, in the sense like a point X, so that's our point here, the fiber, to the Hodge structure to that point. So for example, a family of abelian varieties over a base S is the same thing as a map from S to the moduli space of abelian varieties, ignoring some polarization issues. But in some sense, you see, this is a weird perspective. The family of abelian varieties lives above S, and we want to switch from objects that live on top of S to objects to maps from S to something else. So it's not fully obvious, but it's important in the game. And well, before I need this to introduce this definition. So we want to describe kind of the arithmetic and the algebraic geometry of the Hodge locus. So we say that a subvariety of our base has positive period dimension if its image under the period map is not a point. So that's going to be, I mean, the positive period dimensional one are kind of like in our system, they're not isolated points, but it's like more like points with extra symmetries. They organize on something that has some true dimension. But when we speak of this period map, I mean, it could contract some dimensions. Of course, I mean, like if you were, I mean, even on UND, it contracts a lot of dimensions because I didn't mod out by the PGLN action. So you have to pay a little bit of attention when speaking of dimensions. And so what happens for hypersurfaces, before we saw that for the moduli space of surfaces of degree D, there can be a lot of symmetries on these Noether-Lefschetz loci. So the locus where you have extra symmetry is dense. And they want to tell you, so now I will be, I should have kept D equal to 5. So yeah, D equal to 5 works as well. But not 4, 5. Yeah, maybe, sorry. Maybe I should have written. Maybe you care about the 3, 5 case. Sorry, 5. So you can be a little, I mean, I just wanted to be. So, okay, when you are in this range that the numbers are big enough, so if you may move away from surfaces, in general, the Hodge locus of positive period dimension is going to be algebraic. So rather than being a countable union of algebraic, it's going to really be a finite union of maximal special subvarieties. So the picture, it looks like you have a bunch of isolated points, possibly infinitely many, but then you have just like one big algebraic subvarieties acquiring extra symmetries in a family. So outside that, everyone else has the same amount of symmetries as the global system. And yeah, well, they had some arithmetic applications that it's not so important. So how do we see the Hodge locus? And that's going to be related to also how can it be proven to be algebraic using the period map? So yeah, so what's the Hodge locus in practice? It is so you can define it from the Tanakian perspective, but then I'm telling you the period map is a better perspective. So how do I recover the Hodge locus from this period map perspective? So if I have a subvariety of S, it supports itself a variation of Hodge structure just by reducing V, by restricting V to Y, which gives you also a period map to dy, where dy is kind of a homogeneous space under the amount of global symmetries that Y has. So the Mumford-Tate group of V restricted to Y. And naturally, from this game that we were playing here, these like Y symmetries lie in the global symmetries of the system. And then we obtain a square like this. So that's kind of the fundamental commutative square. So Y is commutative. So Y lies in its own small period domain that lives in D mod GC, and it factors through S. That's true for every single Y, even a point. And Y is special if, in fact, the diagram before is kind of a fiber diagram. So if Y was the intersection, Y is exactly a component of the preimage of psi minus 1 of dy mod gamma Y. So naively, we are thinking that our special subvarieties, our components of the Hodge locus, are the intersection between S, our system here, and the sublinear algebraic objects parameterizing extra symmetries. And let me pause a moment and tell you, like, where does the minimality enter? So if you knew that this guy, but first, are there any questions on this definition? This intersection. So Hodge loci are intersections. So if you knew that this map here is definable, and you knew that this object here, so in this diagram, so I told you that the Catani-Dell'In-Kaplan proves that the Hodge locus is algebraic. So let's say that we work with this diagram in the definable category. So in the definable category. So that's R and X manifold. This arrow here is definable. This arrow is definable. But then the pullback of a definable map is once more definable. So that object here, even if it was a priori living in the holomorphic category, because of the deep fact that this map is definable, it implies that it's also definable. But by construction, it's also holomorphic. So it's a complex analytic manifold inside an algebraic variety, which is definable. So you obtain something that's both definable and complex analytic, and it implies automatically by this kind of or minimal Gaga or minimal Chow lemma, which is not so difficult to prove, that Y itself is algebraic inside S. So that's how it relates, how minimality enters in this picture. So maybe, I mean, I think Bruno stopped right before explaining this, so I thought it was nice to finish the argument. So I hope this relates to the previous pictures. And that was done by Baker, Klingler, and Zimmerman. Any questions on this? Very well. So our Hodge loci are intersections. And then we can play the game that I wrote before, this Bezout/Newton thing, that two lines in a plane should intersect in points, but two lines in a three-dimensional space shouldn't intersect. So how do we formalize it? Well, there's a definition. Well, it builds on the work of many people, but yeah, it was formalized in this setting, in this paper here. So a special subvariety Y is either typical or atypical, simply whether this intersection behaves dimension-wise as expected or not. So typical means that the codimension of y in S is the same thing as the codimension of dy mod gamma y in our big period domain, and atypical if you have a smaller codimension than expected. So, and the Hodge locus is the union of the typical and the atypical components. So we are really recovering everything. And then we'll go back in a moment to the Noether-Lashes example. But before we do that, let's just maybe pause one more second on this definition. So what's happening? So in this cartoon, let's say that S at dimension 2, so that's our base variety. So we have a variation of Hodge structure, let's say encoded in this map P, psi, and we live inside the three-dimensional period domain. And the Hodge locus is made by the red things here. And okay, so we look at y1. So how do we realize y1 as an intersection? So I'm just telling you that I have to look inside the period domain. So I look at my point psi of y1, and I find the smallest subperiod domain passing through this point here. And this turns out to be a line for some reason. So that's my dy1 mod gamma 1. And so the point y1 is the intersection between S and this line. Well, and this is a typical intersection, right? Because I'm intersecting a surface and a line in a threefold, and I get a point. So it's like the codimension of y1 in S is 2. The codimension of this line in this period domain is also 2. So accordingly to the previous definition, this is a typical intersection. Now, what happens to y2? I have to do the same thing, game. So I take the period map, I look inside this period domain, and I look at its image, and I get another line for some reason. So here, the way I compute it is, it's not, I mean, I need to compute the symmetries that exist on this y2. But now something atypical happens, right? Because I have a line, I'm intersecting a line with a surface in a three-dimensional space, and I get a line. So 1 is the codimension of y2 in S, but the codimension of my period domain dy with gamma 2 in the ambient guy here is 2, and 1 is smaller than 2. So y2 in this picture is an atypical intersection. So that's something that we should say, oh, wow, should be rare, right? These points have nothing special here, but this y2 is a gem, is a rare object, and we should have a meaning, and we should investigate it, because it's not so common to find such guy. So there's a conjecture describing this picture here, which is called the completed Zilberpin conjecture. And it tells us that our pair SV contains only finitely many maximal atypical intersections. So the atypical components are rare, and they should appear only finitely many times. Whereas the typical ones should be easy to find, if you can find them. So the following should be equivalent. S contains one typical intersection, if and only if the collection of typical intersections is dense in the space, and if and only if you can find for some reason a typical intersection for like just combinatorial reasons. So to have a typical intersection, you need at least to have a subperiod domain d prime in D, such that the dimension of psi of S minus the codimension of d prime in D is bigger or equal than 0. So that's just like, if you were in the previous picture and there were no lines, every intersection should be atypical. So you need a subperiod domain of dimension 1 to find typical intersection in this setting. Otherwise, there's simply no way. Yeah, and those should be equivalent. And let me go back for a second to the Noether-Lashes locus. So each component of the Noether-Lashes locus is indeed of the form U to D intersecting with some subperiod domain. And these subperiod domains, they have codimension H to 0. So that's where the Hodge theory comes into the game in the ambient period domain. So the ambient period domain is just parameterizing all Hodge structures of type H to 0 with Hodge diamond H to 0, H11, H02. And so you see, what I was calling general components are the one exactly of codimension H to 0. So they are exactly some sort of typical intersection. They should just appear for Hodge theoretic reasons. Whereas the exceptional ones, they were bigger in dimension, and they should appear for some more complicated reason. And yeah, so, I mean, this conjecture implies the result. I'm trying to convince you that this conjecture implies the result I was describing at the beginning on the Noether-Lashes locus. So what's known about this conjecture? Well, if you restrict yourself to the geometric settings, to the positive dimensional part, in fact, the conjecture is known. So there's good evidence, at least for the geometric part. Well, for pure VHS, it was done in this paper of Bruno Klingler and myself with Emmanuel Ulmo. And in the case of variation of mixed Hodge structure, it was done by myself with David Urbanik, and there's also an effective proof on this result. And in fact, there's a new approach. So in the second proof, actually, we don't use minimality, but it's in fact inspired by some work of Gal Bignamini and Chris Doe. They work in a different setting. And also the geometric part of the typical conjecture is also known by this work, as well as work of Eterovich, Scanlon, and Khalifa Urbanik. And both proofs use functional transcendence. And so it's like a large industry of how to get these results. But maybe let me just focus on one case where you know that everything is in fact atypical. And that was kind of hinted before, and it was appearing in the case of hypersurf, in this case here somehow. So when the numbers are big, it's easier to have everything to be atypical. So there's a notion of complexity that you can associate to the Hodge structure called the level. So that's the smallest case. So you have a formula here, but you should think that the level is roughly the weight of the Hodge structure. So generically, an Hn, if you were doing an Hn of some variety, should have level n. So that's the weight is n here, and the level should be n. But sometimes it's n minus 1, something like that, n or. So you have to pay attention a little bit, because the way you compute is more on the adjoint Lie algebra rather than on the Hodge algebra itself. So, but there's a way to formalize it. So this notion of Griffith's transversality gives you a preferred subbundle of the holomorphic tangent space, and then you can just bracket it itself and see how many iterations you need before you get 0. So if you need, so Shimura varieties, the setting where period maps are algebraic, it's kind of the thing level 1. Surfaces of degree D that I was explaining before is of level 2. Unless you're in degree 4, that's why in some cases there was like the assumption degree bigger than 4. If you had surface of degree 2 and 3, they would be of level 0 somehow. So there's a numerology to compute it, but it's very explicit. And the main result in the direction that we proved is that if the level is bigger or equal than 3, then every component of the Hodge locus is atypical. So in this system, in fact, the picture should look exactly like this one. So there's maybe one positive dimensional component in the Hodge locus and 1 point. And maybe more than that, but you're off by a finite set. Please.
Just sorry, the notation that you're using in the formula for the level, G minus 1 is the weight minus 1 component of the. Okay. Thanks.
Yeah, exactly. But yeah, but on the Lie algebra, in fact, so there's a way to identify the holomorphic tangent space of D with something that will look like G minus 1 plus G minus 2 plus G minus K. And yeah, this is somehow the minus 1 part, the 1 or minus 1 part. I mean, it depends. Either you take holomorphic or anti-holomorphic. It doesn't matter, but that's the minus 1 part. The 0 part is kind of the M you get when you do D minus M, and the other guys are kind of the anti-holomorphic. Exactly. But Griffith's transversality, that I don't quite describe it, is something related to these things. I can explain it at the end. But thanks for the clarification. Thanks for your question. More questions, please? Yeah.
Could you give me some intuition about the conjecture theorem Ty?
Ty, yeah.
Yeah.
Yeah, Ty somehow, yeah, in the nota lashes locus it happens. And also Ty is almost known in some sense. So what's the intuition? The intuition is that the intuition comes from, so if you were to intersect two lines in P2, they should intersect in points. And in fact, they do intersect. And here you allow yourself to move things by this Ake operator, so there's some conjugation happening. And in fact, it's like you have two objects of the same dimension, of like, let's say you're in a 10-dimensional space, and you have two objects of dimension 5. And one of the two is kind of moving in a family. So these Hodge loci always move on the right-hand side. And so in some sense, when they move, they foliate the space. They are really kind of going everywhere. So they equidistribute, they are very dense. And then when you have another 5-dimensional objects, and you intersect with this family thing, this intersection should happen. There's no reason why they shouldn't. Well, there's one reason, but I will not tell you which one it is. But so the reason is that the objects in the Hodge locus move in families, and they are very dense. So, yeah.
So when this happened in a dense subset.
Exactly.
Okay, thank you.
Yeah, analytically dense. So it's very dense. So the things that, I mean, they're not quite moving in a family. So the way they move is complicated. But nevertheless, they do move, and they are dense. And also when you pull them back, as long as you pull them back along things that have the expected dimension, they should keep this density property. this feels pretty intuitive, I would say.
Thanks.
At least from a differential geometry viewpoint. I mean, I hope it makes sense. Also in other theories. But this feels believable. So, yeah. Thanks. Okay, so that's the level that was appearing before. Yep. Okay, so a roadmap for the level. So level 1 means a billion varieties. There are also some other exceptional examples. The Noether-Lefschetz locus in degree 4. Level 2 means it is Noether-Lefschetz locus of degree D bigger than 5. Level 3 and bigger means more like other hypersurfaces, Calabi-Yau threefolds. Everything lives in the world of variation mixed Hodge structure. There's other applications. And in general, then the question is like, what do they tell us as before? So what are concrete applications of this viewpoint? And then where it's my endpoint, I hope I had more time, so I will be a bit quick. And so that brings us to the end game, so the link with string theory. And the first time I thought about it, I was like, okay, we should ask ChatGPT. I mean, I had no idea what string theory was, I'm sorry. So I actually wanted to share the picture. I mean, so according to ChatGPT, Hodge theory deals with periodness, variation of Hodge structure. There's a bunch of Hodge numbers. There's the Hodge decomposition. There's something called Perios that I never heard of. And I guess, but it told me Perios, so I don't know. And on string theory, there's closed open strings, D brains, Calabi-Yau, quantum field theory, brains, and so on. But okay, and there's some interaction and some bridge. So it didn't feel so convincing. So I tried again, actually. It's like try to give something less mathematically oriented, and that's what I got. So yeah. So here I realized we really need to meet people from string theory and mathematics, because just me and ChatGPT will never work, right? I mean, it's gonna be a dead game. Maybe I should try with the version where I pay $20 a month, but okay, that seems expensive. Okay, so well, we are looking for a string theorist, and indeed, I mean, I'm gonna give you a quick overview. And I think it would be nice to write actually this connection between the Hodge locus and the string theory. So if someone wants to join me and do the other half, I would be happy to spell out what these examples are in some survey or something like that. Well, just reach out, please. And disclaimer, yeah, I'm not a string theorist, of course. And when I wrote it about it, I was also even puzzled by this sentence in some sense. Like string theory, I should be made of strings, right? That should be right? So in some sense, I know something about strings, right? I mean, so I was like, am I a string theorist or not? I mean, of course. But what is true is I know nothing about string theory. Yeah, and then, yeah, just to give a punchline, maybe it's this family. I mean, and I think many people from mirror symmetry, were considering this. So maybe that's a family to keep in mind where we are interested in the Hodge locus. So the Hodge locus in this thing would mean the lambda where you acquire extra symmetries of the lambda. Yeah, lambda. So what kind of things I've seen? Yeah, so first of all, so there's a link from string theory to Calabi-Yau 3 manifolds. And it seems to be related to, I mean, it is related to conformal field theories. And in fact, there's a conjecture by Gukov and Waffa in 2004 that's a special case of Calabi-Yau of this Zilberping conjecture, and kind of very interesting. I mean, this conjecture was even formulated before we had this Zilberping viewpoint. So we had other viewpoints much earlier in the case of Shimura varieties. So in the case of abelian varieties, the conjecture. So some people arrived to this kind of point of view from the theory of abelian varieties. That's level 1. Other people arrived from this theory of surfaces, from Noether's theory, and that's level 2. But no one from this community considered level 3 and higher, because it seems very difficult. But in fact, from string theory, I mean, people considered the case of level 3. And in fact, there's a conjecture about how many Calabi-Yau manifolds have complex multiplication. So complex multiplication means that your point has the most amount of symmetries. So that the group is the smallest, and it turns out to be commutative. And the link, as far as I can tell, it's related to this paper where they introduce rational conformal field theories. So the extra symmetries here on complex multiplication on the level of your variation of Hodge structure should be related to rational conformal field theories. And then you hope to classify them. And then you hope that there are not so many. And that's related to some things. And that's related to the Hodge locus of some family of Calabi-Yau threefolds. And there's also another approach that I was aware of, and it's done by Greg Moore in 2004. That's also exploring the arithmetic string theory link. And there's something called the attractor varieties that appears in the string theory and also in the study of black holes. And there are two types of like special points from that theory. One is called attractors of type 1, and the other one is called attractors of type 2. And yeah, there were some papers that gave a computational evidence for the finiteness of the two attractors. And in some sense, what's interesting is that, but maybe there's, well, let me say one thing. What's interesting is that these attractor points, they are not quite CM points. So CM points are the most extreme symmetries, but these attractor points turn out to be atypical intersections, but of 0 dimension, but atypical in the true sense. So CM points are essentially always atypical, unless you're inside a moduli space of abelian varieties. But yeah, so somehow to discover some more subtle Hodge theoretic subtle examples of atypical intersections is not so easy to find it in practice. I give you this Noether-Lefschetz example. But in fact, here, there were some other examples. That's quite remarkable. So there are some computational evidences. There's also a paper of Josh Lamb and Tripathi from 2004 that also assumes the Zilberpin conjecture and shows that there are attractor Calabi-Yau varieties in all dimensions different from 1, 3, 5, and 9, which are not defined over Q bar in some sense. So there's one type of attractor points, the type 2, that's fully described by Hodge theory. There's another type not quite described by Hodge theory, but nevertheless, there's like once more a link with the Zilberpin conjecture, which would imply that there are like some attractor points not defined over Q bar. So it feels quite a rich theory. And finally, there's the work of Grimm and Van Heijsteg from 2004, where there's a new application of this. Well, I will not, it's related to flux vacua, but I mean, I will not dare to comment. But nevertheless, there's a new setting where Hodge theory encounters modern string theory compactification, and where once more this atypical condition on the Hodge locus enters in the picture, and that seems very exciting. And probably there are other examples in the literature, but I try to just collect what I was aware of and what was around in 2004 and 2024, and somehow everything fits in the fully Hodge theoretic paradigm that we were describing. But yeah, so I will stop here. Thanks for the attention.